Hi everyone, just we're running through your feedback questions. How do you calculate formal charges and how do you identify which are bonding, non-bonding, or valence electrons? So I'll actually start with that last one. How do you identify which are valence electrons? At least in the Lewis structure, everything is a valence electron. That's what you draw or represent in a Lewis structure are only the valence electrons. How do you determine how many valence electrons an atom has is by its position in the periodic table. So very roughly speaking here, you guys should all have some periodic table. And very basically, you guys can see here at the top of the column, there should be, so these in particular have, actually this one's not focusing. Anyway, fluorine should have 7 valence electrons, and you can tell because it's in the column 17, or more specifically column 7A. That 7A is how you know it has 7 valence electrons. Alternatively, you can count over and recognize, okay, when you're filling up the electrons on the Aufbau principle, you go through the s block and then the p block. So this would be 1s2, 2s2, so there's 2s2, 2 electrons in the 2s orbital, and then 5 electrons in the 2p orbitals. So the valence electrons are the outermost electrons in an atom. So for fluorine, it's 1s2, 2s2, 2p5. These are the valence electrons because they're in the outermost shell. They have the highest principal quantum number. So there's 2 plus 5, so there should be 7 valence electrons for fluorine. So you have a couple of ways for figuring out how many valence electrons an atom should have. How do you calculate formal charges? Yeah, you need to know the number of valence electrons, the number of bonding electrons, and the number of non-bonding electrons. So we define formal, actually let me put this over here. We define formal charge as being equal to the number of valence electrons an atom would have in its non-bound state. So for fluorine, that would be 7, minus the number of electrons it has in non-bonding or lone pairs, minus the number of electrons it has in bonding pairs. So I'll give you guys a quick example here. HF you know what? That's fine. So HF, hydrogen normally would have have 1 valence electron. Hydrogen has 1 valence electron. It only has 1 electron. So if I wanted to assign this guy a formal charge, it normally would have 1 valence electron. It has no electrons in non-bonding pairs. You identify the number of electrons in non-bonding pairs by these dots. Each of these dots represents 1 electron. So hydrogen has no lone pairs, so it has 0 electrons in non-bonding pairs. And we represent bonding pairs. This dashed line, or rather this line, represents 2 electrons. So each of these dots represents 1 electron, and the shared pair represents 2 electrons. So hydrogen in this particular Lewis structure has 2 electrons in a bonding pair. So I'll take half of them. The idea is that if you assume that these 2 electrons were shared evenly, half of them would go to the hydrogen and half of them would go to the fluorine. So I have 1 minus 0 minus 1, 0. So this hydrogen has a formal charge of 0. On the flip side here, fluorine normally has 7 valence electrons. It has 1, 2, 3, 4, 5, 6 electrons in non-bonding pairs, and then it has 1, 2 electrons in a bonding pair. And again, the idea is it gets half of those. You assume it's those shared electrons are shared evenly, so the fluorine gets 2 of them. So I have 7 minus 6 minus 1. So this fluorine also has a formal charge of 0. So this is a perfectly happy molecule with no formal charges. How do you always set up Lewis structures the way it's given? For example, CNO, and I told you, okay, like for example today, there was ambiguity about how to order and arrange the atoms in the Lewis structure. And I said specifically, okay, one of them looks like this, CNO, and the other one looks like this, NCO. Can you always predict the Lewis structure, the basic skeletal structure, based upon the chemical formula and the way it's written? No, unfortunately. You frequently can make that assumption, and sometimes we will try to write chemical formulas so that they imply the structure, but it's not a clear-cut thing. So obvious example is something like H2O. The Lewis structure for this is not HHO. It's definitely not that. There's two reasons. Well, there's at least one reason. I'll just point out one reason why it's not this is, we'll take a second here and think, pause the video and see if you can figure out why this Lewis structure is no good. Reason why it's no good is because hydrogen here is violating not the octet rule, but it's violating the duplet rule. Hydrogen normally can only fit 2 electrons in its valence shell. Here, hydrogen has 2 electrons from one bond and then 2 electrons from the other bond. So this hydrogen has, as drawn, if I checked its formal charge, it would be, well, normally hydrogen has 1, no electrons in valence shells, or in non-bonding pairs, and then 4 electrons in bonding pairs. So it has a formal charge of -1, and basically hydrogen just can't fit that many electrons. It can only fit 2 electrons into its valence shell. So there is a general trend. Generally, you put the least electronegative atom in the center. That is a general trend. The least electronegative atom goes in the middle as your central atom. But that's not always going to be the case. And so it is, to some extent, a case-by-case basis, and really the only way to get instinct about that is to do as many examples as possible. So I would encourage people to look through the homework problems, do all the homework problems, and then work through the suggested problems as well, to get as much experience as you can doing Lewis structures, so you build up some instinct about how many bonds a molecule should make. How is oxygen sharing 2 electrons in CNO if one electron is from nitrogen and the other one is from oxygen? So let me draw out this. So the question is, how is oxygen sharing 2 electrons if one electron is from nitrogen and the other one is from oxygen? So you're looking at it like this way. You said, okay, nitrogen has a half-filled, has one unpaired electron. Oxygen has an unpaired electron. The idea is if they share them and make a bond, they can make a bond and they can fill up their octets. They can fill up their valence shell. So generally speaking, how is it that an electron is sharing 2 electrons? Anytime you see a line like this, it represents 2 electrons being shared. Yeah, I feel like we normally teach Lewis structures from this perspective. Oh, if you come in with these half-filled orbitals or half pairs, you can make bonds. That's how you normally teach Lewis structures, but I think if anything it kind of confuses students because it gets you into thinking that's how you should be constructing Lewis structures every time. And really, you shouldn't try to construct Lewis structures like this. Don't just do this. Say, okay, nitrogen should have 5 valence electrons, 1, 2, 3, 4, 5, so I can make 1 connection there, I can make 1 connection there, and 1 connection there. Don't think about it like that, or don't approach drawing Lewis structures in that way. The better way is the algorithm, the guidelines that I presented to people on Friday, and that you can also find in your textbook for actually writing Lewis structures. We teach this way to sort of conceptually teach what's going on with the bond, that you are sharing a pair of electrons. And again, the idea is these 2 electrons are sort of shared between the oxygen and the nitrogen. And that is how we conceptualize the bond being formed, but when you're trying to plan out how to draw a Lewis structure, don't draw it like that. Follow the algorithm. How do you know that CNO fulminate has this Lewis structure and not this Lewis structure? Something like that. How do I know it's this structure but not that one? How do you know that any structure is the preferred Lewis structure? You assign everything a formal charge, or you check the formal charges for each of the atoms in the molecule, and then you judge or assess it by the criteria that a molecule is stable. In the Lewis model, it's stable or preferable for it to have small formal charges and as few of them as possible. So in this particular configuration, I'm not going to calculate it. I'll tell you what the values are, and I encourage you to check and prove to yourself that they should have these values. The Lewis structure in this Lewis structure, the formal charges are 0, +1, and -2. So this one is a little bit, and in this structure we said it was -1, +1, and -1. So which one of these is better? Generally, again, you want the smallest formal charges possible and as few of them as possible. So yeah, this one has more formal charges, but this one has a larger formal charge. And especially it puts a very large negative formal charge on carbon, which is not very electronegative. It doesn't really want to have a -2 charge. Coincidentally, oxygen is fairly electronegative, so it's not terribly unhappy having a -1 formal charge. So that's okay. This one is not good because it has a very large negative formal charge. Yeah, it has fewer formal charges because here it has 2 formal charges total. This one has formal charges on everything, but the magnitude of the formal charges are larger in this molecule. So this one is unstable. Also, you said electrons are being forced onto the carbon atom. Then why are the arrows drawn away from the carbon? The way I've drawn it here. I said, okay, the arrow is drawn this way. I said that the electrons are being forced onto the carbon. When I say they are forced onto the carbon, I mean that we, by drawing a Lewis structure and trying to distribute electrons and fill up octets, we have forced more electrons onto carbon than it would prefer to have in the context of formal charges. Formal charges on carbon, normally it would prefer to have 0 formal charge. And I have forced an additional electron onto carbon. Here it has 1, 2, 3, 4, 5, and normally it has only 4 valence electrons. We, by constructing this Lewis structure, have forced electrons onto it. This arrow, the arrow showing the pull of electrons, that's not how electrons are forced. That's not how we are forcing them. That's how they are naturally compelled to be moved by following electrostatics. Nitrogen has a larger effective nuclear charge than carbon does, so it tends to attract electrons towards it more, hence it has a higher electronegativity. So physics forces the electrons that way. We, the chemists drawing this Lewis structure, have forced electrons onto carbon in order to make all of these bonds and give everything an octet and try to minimize our formal charges. We have forced the electrons there, and that's not good. You said that the best Lewis structure has the smallest number of formal charges, so do you mean smallest number or closest to 0? Short answer, both. You want them to be as close to 0 and as few of them as possible. Fewest number of formal charges and the smallest magnitude of formal charges. And if you have to choose between the two of them, which one is better? It's better to have more formal charges but small in magnitude than it is to have a few formal charges but relatively large in magnitude. So both factors need to be considered. And in general, neither one is good, but if it's a toss-up between the two of them, you choose smallest magnitude of charges. I understand the concept of formal charges and Lewis structures, but is it expected of us to use formal charges to construct Lewis structures, like the way you did for fulminate and cyanate? Are you guys expected to use formal charges in your construction? I would say yes and no. You're not expected to use formal charges. I would request, or I would suggest, that you check formal charges. We use formal charges as a way of assessing or judging how good a Lewis structure is. So when you're first starting out and you're trying to get a good sense, okay, what is the proper way to write a Lewis structure for a molecule? There's a general guidelines, which I presented. You determine how many valence electrons there are to distribute. You draw a basic structure, and then you distribute electrons around it to fill up valence shells, to fill up octets. But there's multiple ways you can do that, and I've given a few homework problems to this extent. There are multiple valid Lewis structures where everything is connected and everything has an octet, but some of those are not good structures, or they're not the best possible structures. And the way you assess them, what's a good structure or what's a bad structure, is on the basis of formal charges. So I would not say that you are expected to do that. I would recommend and say that, yeah, as if your goal is to find the best Lewis structure, then yeah, it's probably the best thing to do is to check formal charges. Do I expect people to do that? Possibly. Depends on, I mean, I know students usually are concerned about, excuse me, are most concerned about what I'm going to put on an exam question. If I expect people to find formal charges, I'll ask you to find formal charges. I might give you two molecules and say, okay, which of these is better? Or give you two Lewis structures and say, which one of these is better? And the way I expect you to decide which one is better is on the basis of formal charges. So in that sense, yeah, I expect you to calculate formal charges. But if I just give you a molecular formula and say, what's the Lewis structure, it's implicit that you should probably check the formal charges to figure out how good your own predicted Lewis structure is. What's the point of using formal charges if we use electronegativity to draw dipoles? Is it to find the best Lewis structure? Yeah, you answered your own questions. You don't use formal charges to predict dipole moments, so that's when this is right here is sometimes called a dipole, because we say that there is a partial. The formal charges are not real, they are fictitious, but these partial charges are real. There is a partial, we expect there to be a partial positive charge on the carbon and a partial negative charge on the nitrogen. This is the Greek symbol delta, and essentially in mathematics we use delta to mean a little bit. So that's where it's called a partial charge. It's not a full charge, it's not a full -1, but it might be 0.53, negative 0.53. So it's a partial charge. And those partial charges are real. These formal charges are not real charges. Those are formal charges that come up as the result of checking the Lewis structure, but the Lewis structure is not 100% real either. But these partial charges are real. So you assign partial charges and dipole moments with electronegativity. The point of formal charges is to assess which Lewis structure is best. That's the only context in which you should ever think about formal charges, is if you're trying to assess the goodness of a Lewis structure. Dipole moments, electronegativity, that will come up if you're trying to assign electronegativity will come up if you're trying to assign dipole moments, decide whether a bond is polar or ionic. You can use it to assign oxidation states. So electronegativity is more valid, or rather more useful, but I did want to introduce formal charges because I didn't get a chance to talk about it on Friday. Why does the fulminate ion even form normally in the environment if it's so unstable? It's like forming an upside down pyramid. Yeah, you're right. It doesn't form naturally in the environment. And in fact, it was not so much that Liebig was actually studying it, like he found it and he decided to study it. He synthesized it through a series of chemical reactions. Carefully controlled chemical reactions. Silver fulminate is, so we would say it's friction sensitive. Like if you jostle it too much, you bump it too much, it will explode. So you can synthesize it by, I looked this up because I realized I didn't know how to synthesize silver fulminate. You can synthesize it by dissolving silver in nitric acid and then adding ethanol as a carbon source. So the point is, it's synthesized in a very, very careful experimental lab setting. It's not found naturally in the environment, because if it were ever to be synthesized in the environment, it's probably going to be in very, very small quantities and by some um, very specific niche biochemical reaction. And I don't know any chemical reactions that would make use of the fulminate ion. So the short answer is that no, it wouldn't be formed naturally in the environment. Liebig synthesized it very carefully. How is it possible that krypton and xenon have electronegativity values? Okay, that's actually an interesting question. I didn't point this out on the chart of electronegativities. Most of the noble gases don't have electronegativities, and that's because they don't form bonds. Electronegativity is defined in the context of chemical bonding. It's how much an atom tends to gain electrons while it's forming chemical bonds. If you make a bond between carbon and nitrogen, which one of these is going to pull electrons more towards itself? Most of the noble gases don't even make bonds. They are chemically inert. They don't react and form compounds. So most of them don't even have electronegativity values, except for krypton and xenon. Krypton and xenon are actually capable of forming a few very weak bonds. And part of that has to do with simply how large the atoms are. The electrons on the outermost valence shell of krypton and xenon are very, very far from the nucleus. They have these big electron clouds, and we say that that electron cloud is very polarizable. You can pull electrons off of it, you can deform it, and it's just because it's so large and there are so many electrons there. So krypton and xenon are actually capable of forming a few compounds with, well, think about this. Krypton and xenon are at the bottom of the periodic table. So they should have the lowest ionization energies of any of the halogens. So you can pull electrons off of them. And you can, for instance, form compounds like xenon tetrafluoride. And you can make compounds with xenon basically with only fluorine. And that's mostly because fluorine's electronegativity is so high. Its electron affinity is so high. It really likes to steal electrons. Xenon is capable of donating electrons because its electron cloud is so large, so it is capable of forming some very weak bonds with fluorine. And because it's capable of forming bonds, you can assign it an electronegativity value. Helium, neon, and argon essentially are chemically inert. They don't form chemical bonds, so it doesn't make sense to assign them electronegativity values. Electronegativity values only make sense in the context of a chemical bond and how electrons are pulled or unevenly shared in that chemical bond. In CNO, so let me continue here, the dipoles don't match the way the charges are facing. So I have one dipole that points this way, and I have another dipole that points that direction. Does that play a part in the stability of the compound? Yes, generally. I mean, I won't say that's the only reason why. You can have molecules with a net dipole, and that net dipole is perfectly fine and stable. It's not that they're both pointing in the same direction that makes it unstable, that all the electrons are shifted to one side. What makes it somewhat unstable is that we're trying to force electrons, or we need to force electrons onto carbon in order to we need to force electrons shared towards carbon in order to make this triple bond, which is unfavorable. And it's especially unfavorable considering that, if anything, the electrons should be shifted onto nitrogen, not shifted onto carbon. So I would say it's only partly related to the fact that the dipoles are pointed in the same direction. How does electronegativity determine the attraction of atoms? Okay, so generally speaking, and again, this is a broad generalization, if two atoms have very different electronegativities, their bond tends to be a little bit stronger, very generally. So I'll give you an example. Nitrogen, N2, is a very chemically inert compound, does not react with much, which is good. For instance, we're breathing in. Most of the air we breathe in, we don't actually make use of. Most of the air we breathe in is nitrogen. And it's a good thing that it's not reactive. Otherwise, every time we breathe it in, we would be doing undesirable chemistry in our lungs. So it's very, very stable, partly because it has a triple bond, and that's good. So it has a very, very strong bond. It doesn't break easily. A compound with an even stronger bond is carbon monoxide. And that bond is even stronger because it has a partial ionic character. Atoms are held together by electrostatic forces. Opposite charges tend to attract each other. So oxygen is more electronegative, so you end up with a partial negative charge on the oxygen. Carbon here is partially positively charged. Wow, that's not a partial, that's not a delta. It's partially positively charged, and those partial charges tend to attract each other and hold each other on. The extreme case of this is if I had, say, oxygen and calcium. Oxygen and calcium. In the extreme case, so this would be a nonpolar bond, this would be a polar bond, this would be an ionic bond. Ionic bonds generally are stronger than covalent bonds because you have full attraction of charges. Here I have a negative charge, a partial negative charge, and a partial positive charge, and those guys are attracted to each other. Here I have a full positive charge, and I have a full negative charge, and those full charges are attracted to each other. So very generally speaking, bonds are stronger between atoms if they have differences in electronegativity. That is a gross generalization. It's not always going to be the case. Here's an example where that's not actually enough of a factor. So very, very broad generalization. Can you post the answers to the previous midterms so that we can study for the final more efficiently? Yes, I sincerely apologize. Normally I do post the solutions. I've been reticent to do so this semester for some reason, but I will definitely post the solutions to the midterm for the upcoming final so people can study. All right, other than that, I thank you everybody for your feedback. I love getting feedback from people, so this is great. I will see everybody possibly today or later today or Tuesday for lab. Otherwise, I will see everybody on Wednesday, where we will continue talking about some of the details of Lewis structures and charge distributions. In the context of Lewis structure, we're going to be talking about resonance and exceptions to the octet rule. So I'll see everybody on Wednesday. Have a good day.